Hello students, in this lecture we are discussing pumping lemma for regular languages. I assume you have already know about deterministic, non-deterministic finite automata, regular language and relation between them. So the question is, are all languages regular? No, most of the languages are not regular. Uh, Regular languages are recognized by finite automata. So how we can differentiate between regular languages and non-regular languages? Here the role of lemma, pumping lemma comes. To begin with, we got a theorem that if a language L is finite, then L is a regular language because it can be recognized by an finite automata. Then what about infinite languages? Like the examples given here, L equals to 0 n repetition and 1 m repetition, where both n and m are greater than 0. In the other example, 0 n repetition and 1 m repetition, where m is greater than. In first example, the n and m variable are not related, but in the case of second example, n and m are related. So what this relation means, the number of repetition of 0 and the number of repetition of 1, we have to maintain a memory where we have to count the number of zeros and number of ones, and the number of zeros should be less than number of ones. If we want to generate a finite automata which recognize this language, then we have to memorize the number of repetition of 0, and we have to generate a substring of 1 which have more number of repetition than number of zeros. To recognize such a string, we need a automata which has infinite state. But in case of finite automata, we have limited number of states. So we can say here that this regular this language is not a regular language. To systematically classify regular language and non-regular language, we use pumping lemma. Any language that satisfies the lemma is classified as regular language, and the language which does not support the lemma or satisfy the lemma is classified as a non-regular language. Idea behind pumping lemma is to divide the regular expression or the regular language into three parts: x, y, and z, where x and z are non-repetitive part and y is the repetitive part. The finite automata here should reach from initial state to final state, where from the initial state, when the x substring is given, it reaches to the intermediate state R, where it turns n times for each y repetition, and after encountering the z substring, it reaches to the final state. So such finite automata accept any regular expression of infinite length which has y repetition, y substring has n repetitions. So again, here y is the part which can be pumped into the system or finite automata n times, and still the automata reaches the final state. So it can be seen here that if for any regular expression or a regular language such xyz exists, then it can be classified as a regular language, and if no such xyz exists for the language, it will be classified as a non-regular language. Here the idea of pumping lemma is formally defined. If L is regular language, then there is a number of n such that any string w belongs to L, where w is length of string w is greater than or equals to n, can be divided into three parts: w equals to x, y, z, such that length of y substring should be greater than 0, x, y length of xy substring should be less than or equals to n. For each I greater than equals to 0, x y raised to power I z belongs to regular language L. So informally, it can be discussed as the regular language has three parts which consist of length n such that any string of length more than n can be pumped. The pumped part y should not have length 0. It means it should have at least one character or one letter. The part before and after the pumpable part y, that is x and z, can be null. To understand better what we have just discussed, let's take an example where language A is equals to A, B star C. It can be represented by the finite automata having three states Q0, Q1, and Q2, and the transition diagram is as shown here. Each word in L consists of a path from Q0 to Q1 followed by n repetition of uh, path to Q1 itself and then a path from Q1 to Q2. Any word W or a string W which belongs to L here can be divided into x, y raised to power I, and z. And since it satisfies the x, y raised to power I and z, we can say that it is a regular language. In this next example, we can say a simple finite automata which is a single state Q2, which is the initial state, the final state, and all the input represent back to itself. So it also satisfies the uh, pumping lemma as x and z are null here. So basically, pumping lemma is not used to prove that a language is a regular language. It is, on contrary, it is used for proving that a language given is not a regular language. In order to do so, we first assume any language to be regular, and then we find an x, y, and z substrings and put the properties of regular language or pumping lemma on that, and if x, y raised to power I, and z satisfy those conditions, we can say that that language is a regular language. But on most of the cases, it does not satisfy the pumping lemma, and that's how we prove that it is not a regular language. We will take some examples. So the first example here is L, a language L equals to 0 m repetition, 1 m repetition when m is greater than 0. It simply represents that there is a string, or we can say all the strings with equal number of zeros and equal number of ones are will belongs to language L. Let's assume a word W which is equals to 0 raised to power n, 1 raised to power n. It means W belongs to language L and the length of W is greater than n. So by pumping lemma applying on the uh, string W, we can divide this W into three: x, y, and z. So here the length of x is s and length of y is t. It is represented here in a diagrammatic form of a string of zeros and ones. So the first s number of zeros are part of x, then the two zeros are part of y, which is of length t. Here t is 2, and the remaining will be a string of part string of z. So here, by applying pumping lemma, if we repeat the y part n times, uh, here we have taken I equals to 2. It means we are repeating the y substring twice. So it is represented as 0 raised to power s, 0 raised to power 2t, 0 raised to power n minus s minus t, and 1 raised to power n. By clear, uh, it is very obvious here that number of zeros after this repetition of y will be more than number of ones. So the the string which we get after x y raised power 2 z will not follow the rules of language L, which says that number of zeros and number of ones should be equal. So after applying pumping lemma, it is clearly uh, it is very clear that it does not belongs to a regular language. Here, let's take one more example where language L is given as 0 raised power m, 1 raised to power n. That means for m and n repetition, where m is greater than n, it means a language which have more number of zeros than one. So a string w can be represented as 0 raised to power p plus 1, 1 raised to power p. Here p plus 1 is greater than p. W here can be split into x, y, and z. These three parts uh, can be separated out from the language L. Any word, any string W, and suppose we are uh, giving y. Yeah, we are considering y as a string of zeros. So as we know, y if we split w into x, y, and z three part, y can have a power I, where I can be 0 or any number of value. If we consider I equals to 0, the number of zeros will reduce, and the relation where m should be greater than n will not satisfy anymore. So the resultant string will not support the language L, and therefore we can say that the language L is not a regular language. You have to understand this, that there can be n number of problems uh, in the examination or in books which represents different languages, and they all these questions have same problem, that you have to identify or you have to prove that the language given to you is not a regular language. So for that purpose, you now know how to use the pumping lemma. This is the way we can define pumping lemma for regular language.